We're in section 4.3 at the top of page 10. It says in summary, to find where f of x is increasing, we need to find where the derivative is positive or above the x-axis. To find where f of x is decreasing, we need to find where f prime of x is negative or below the x-axis. And we have an example right below that says graph the derivative f prime of x equals, and we have a function to determine where f is increasing and where it is decreasing. Careful here because they do ask about where the function is increasing and decreasing, but they want us to graph the derivative. So first thing is, since we have the derivative, we are able to find our critical values by taking that and setting that equal to 0. Our derivative is already factored out, so we're going to get x is equal to 0, x is equal to -2, and x is equal to 1. And these right here are our critical values. Critical values are also our x-intercepts. And we should say the x-intercepts of your derivative function graph. And from here, we're going to take a number line. We're going to break it into intervals based upon those critical values. The domain for this function is all real numbers, and I should have said that there is no places where our derivative is undefined. So we have no additional critical values. So splitting this at -2, at 0, and at 1, we need to test values that are in each of these intervals. So I'm going to go ahead and test f prime of -3, f prime of -1, f prime of 0.5, and f prime of 2. Again, picking a value that's in each of those intervals to test, and then substituting that value into your derivative. I'm going to write down the values that I have, but again, check to see if you can get those on your own. So the first interval, we have a negative value. That means that our slope of our function is decreasing, but the graph of our derivative, which is what it wants us to graph, it wants us to graph our derivative. That means that it's going to be below our x-axis. The next interval here is positive. And that means that we have a positive slope for our original function. However, the graph of our derivative is going to be above the x-axis because it's positive. And then the next one is likewise, it's negative, and it's going to be below. And the last one is positive, and it's going to be above. And don't always assume that it's going to alternate like this because it doesn't. So the next thing is it wants us to graph, and then it also wants us to determine where f is increasing and where f is decreasing. So let's go ahead and graph first. And I'm going to go ahead and put our x-intercepts on. So we have an intercept at -2. We have one at 0. And we have one at 1. And again, we are not graphing the original function, we are graphing the derivative. So that first interval is below. And then it switches to being above, so something above. And then the next part between 0 and 1, it is below. And then that last interval from 1 on is above. Again, we can't figure out right now at this time the exact function, but this is the graph of the derivative. Okay, it also asks for where is our function increasing. And the function is increasing where we have a derivative that is going to be positive, which is here and here. So it's going to be increasing. So f is increasing from -2 to 0, union 1 to infinity. And then f is decreasing, where it is negative slope, which is going to be from negative infinity to negative 2, and from 0 to 1. It's where the graph of our derivative is below the x-axis. So negative infinity to negative 2, union 0 to 1. It says, note this does not mean that f of x is increasing on the interval from a to b, then the derivative is positive. There's a counterexample here I'll leave for you guys to kind of look at on your own if you have some time. So I'll leave that for you guys to look at. The next thing that we have down here is concavity. So we have concave up and concave down. So give those both a star. Concave up is if the graph of f lies above all the tangents on the interval. A function is concave up on an interval if it's opening upwards. And concave down, it says if the graph lies below all the tangents of the interval. It says a function is concave down on an interval if it's opening downwards on that interval. So opening up, and if you were to draw tangents, you can see that a little bit better. This is, the graph is always above it, so it's concave up. Likewise, your tangents are above the graph on all of those if you were to draw them, and that's concave down. If you notice, there's another thing on this picture. It's an inflection point, and that's where the concavity is changing. It's changing from concave up to concave down. So point of inflection. The point, once you guys realize it is an ordered pair, is an inflection point. Again, ordered pair. If f of x is continuous at x equals c and the concavity changes at x equals c.